Okay, so let's just get started. The camera on. Okay, good. So we'll start a new topic today on distributed file systems. There were a couple of slides that I skipped last time towards the very end. I decided to put them into the last lecture, which is going to be Internet of Things. So that material will be covered, but it will be covered in a few lectures from now. Okay. So we'll just end the discussion from last time where we stopped, and then we'll start a new topic here, which is on distributed file systems. Okay. So what I'm going to do today is first do a very brief review of Unix file systems. This is topic that you probably have encountered in a undergrad OS class. I'm just going to do a refresher so that the rest of the discussion, which is actually going to be on distributed file systems, will make more sense. Okay, so today we'll do a review. I'll talk about high-level issues in distributed file systems. We are going to look at the first one, which is the network file system, or NFS. Okay, it's a very old file system that's been out there for a really long time, but it's instructive to start with that one. Okay, and then next time we'll continue the discussion and look at 4 other file systems that are distributed in some shape or form with CODA, XFS. We'll look at log structured file system maybe briefly. I'll talk about things like HDFS, object storage systems, and so. Okay, that's next time, but today we'll just start with the introduction and work on understanding NFS. Right. So without further ado, let's just do a quick recap of what a file is, what a file system is, and then we'll get into distributed file system. Okay. A file is essentially a named collection of logically related data. That's a textbook definition. And you all know what a file is. You interact with files on a day-to-day basis on your computer. So essentially, it's a container of data that you store on your computer storage. It has a name associated with it, which is what you as a user use to access files, or that's how you access files in your programs. Okay. Internally, as far as the OS is concerned, files are numbered. Okay. They actually, the name that you give is only used to map that file name to an internal number, and then all operations internally are actually you use that file number. I will get to that in just a moment. Okay. Now, as far as a file system is concerned, okay, it's a component of the OS that allows you to access your storage. Okay, and it provides this abstraction of a file to make it easy for you to create data on your machine, modify it, and so on. And the file system also has other abstractions which allow you to group files, which are directories. Okay, the directory structure is hierarchical. So you have a root directory, your directory is in that root, and then subdirectories, and so on. So you essentially have a hierarchical structure that allows you to create and organize files in your on your disk. Okay? So the file system is providing a easier to use interface to your disk. It takes care of mapping file data to disk blocks. You don't have to worry about you create a file, where on your disk should it be stored. None of that. The OS and the file system will allow you to manage your files without dealing with this low-level data. Okay? And one last piece is files allow you to share data across users. So file systems have file sharing mechanisms that control who can see your file and who can access files, and so on. So essentially, the file system is also going to provide protection. Okay? So those are some basics. We'll now do a quick review of a Unix file system, which is not a distributed file system. That's a typical file system you will find on any Unix-like operating system, Linux, as well as to some degree on Mac OS. Windows file system is somewhat different, but high-level concepts are similar. Okay? So in the context of a Unix file system, Unix treats files as if they were just a sequence of bytes. Okay? It does not assign a structure to a file, and Unix file system do not interpret the contents of a file. Okay? There are other file systems where the file actually has a defined structure, and you have to create data using that structure. And some of these file systems are used in database world, where the structure defines the structure of tables and things of that. Okay? As far as Unix is concerned, none of that is true. Every file is just a sequence of bytes. Okay? whether it's a source code file, whether it's a binary objects, whether it's a Word document, PowerPoint file, image, video, doesn't matter. Everything is just a sequence of bytes. The file may have structure, like a video will have a sequence of images, but the OS does not know about it or interpret it that. Okay? That's an important thing. We'll come back to that. Okay, and directory is essentially a special file that's just a table, and it essentially lists all the files that are contained in that directory or folder. Okay? But as far as Unix file system is concerned, it's another file, just a special kind, that this has a list of other files that are in that directory. Okay? And the file structure is hierarchical. You start with the root directory and your subdirectories and so on. Okay? And these are directoric acyclic graphs, not a tree, but a directoric acyclic graphs. Okay? The reason for this is you can essentially create links between files, both hard links and soft links, that allow two files to have the same name, that allow two directories to have the same name and so on, which makes the structure not quite a tree, but a DAG. Okay? But you can't have cycles in the graph, because if you have cycles in your directory structure, bad things happen. If you start a backup program, it will never terminate. It will just keep going through a loop, not knowing when to stop. Okay? So it is, you restrict the structure to a DAG. And that's all I'm going to say about that here. But as far as the directory is concerned, I just said it was a special file. You will see that it has essentially a file name and an inode number. The inode number is essentially the numeric ID of the file on disk. Okay, so essentially you have metadata on your file system. In case of Unix file system, that metadata is called an inode or an index node. Metadata is data about the data. Okay, so in the inode or the index node, you will keep information like the name of the file, the owner of the file, the size of the file, last creation time, all of the information that is relevant to the file itself, but not the file contents themselves. Those are actually the data of the file, and the metadata stores all of this other information. Okay? So you have the structure, they're numbered, and essentially the file number is essentially the number of the inode that is used to keep metadata of that file. Okay? So you essentially have a file name to an inode mapping, and that mapping is essentially stored in your directory. Okay? Now I should mention that all of these inodes, which is metadata for the file, are stored on a special location on disk, which is called the super block. Okay? Your disk is a collection of blocks. Okay? There are regions of the disk that are marked as special blocks. Those are called super blocks. All the metadata information is kept there, and all the other blocks are essentially data blocks. Okay? And that is where you'll actually store the contents of the file. Okay? So that's something you want to keep in mind. So I can show you a quick picture here. So essentially, if that's your linear, you can view the disk as just a linear array of blocks, although it might be stored in different format. Maybe the first few blocks are going to be inode blocks, and then the rest are essentially data blocks. Okay? And inodes are going to be kept on this special location because it is important for the file system to know how to track down the inode of a disk in order for it to figure out where the blocks are stored. Inodes will have pointers to data blocks. So to first get the metadata, then you can get to the data. But you have to figure out where the metadata is stored. And if you store it in a well-known location, you know where to go and look for it. Okay? That's the reason you're going to keep your inodes in special location on this. Okay? Here is the structure of the inode. Yeah, so you will see that it has all kinds of fields: owner name, group ID, the directory that contains this file, protection information, which in Unix is read, write, execute permissions for the owner, group, and world. And your last modified time, last write time, last time the inode was modified, the size of the file, and so on. And then at the end, you have this array of addresses, and that's really where you have pointers to disk blocks. That's how you are actually going to go and access your blocks of the file. Okay? So the way you want to think about it is, here's your inode structure. So the first few fields are essentially going to be this information, right? And then you are going to have an array, which is going to be pointers to disk blocks. Right? So think of that as your disk. So you're pointing to different blocks on the disk. Okay? So if you want to go access the first block of the file, you're going to go access the inode, look at the first entry that has a disk address, you go look up that disk address, then you know where to go and find the first block. You want to address the second block, you look at the second entry and so on. Okay, that's how you're going to essentially, it's an array of pointers. Each pointer has a disk address. So the ith pointer is the address of the ith block of the disk. Okay, now is that clear? Let's again recap. Now, the thing I'll mention is that it is not a single level index, it's a multi-level index, okay? Which means that since your files can be quite large in size, if you just keep all of the information as a single level index, this inode size is going to grow significantly based on the number of blocks in the file. Okay, so the way this works is the way this is going to work is our inode structure. Here, let me draw a new one here. Okay, we'll have some entries. Okay, the first few entries are called direct blocks or direct entries. So they just have direct pointers to disk blocks. Then you have something called a single indirect block where you essentially point to a block which is itself going to have pointers. Okay, so this entry will have pointer to another block that has another 1,000 entries for disk addresses. Okay, so if your file size grows beyond 10 or 11 blocks, you create a single indirect block that has 1,000 entries. If it grows beyond those 1,000 blocks plus these 12 blocks, then you essentially have something called a double indirect block, where you are going to create a block. Each of those entries is going to point to a block, and each of those will actually point to disk. Okay, so if you have 1,000 entries here, and so this will have 1,000 other block entries, each of them have 1,000 pointers. You have 1,024 squared disk blocks you can store in a double indirect block. Okay, and if you grow beyond that point, you have something called a triple indirect block, where this pointer in the inode is going to point to a block that has a set of addresses. Each of those point to another block that has a set of addresses. Each of them point to a third block that has a set of addresses, and those are the ones that point to a disk block. So it's a pointer to a pointer to a pointer to a pointer, which actually eventually points to a disk block. Okay, that allows you to get to 1024 cube blocks. Okay, so if you look at this inode structure, you will see that it essentially allows the files to grow to large sizes, and it allocates one level of indirection, has 2 levels or 3 levels of indirection, depending on the size of the file. Okay, very large files might require you to do multi-level lookups in order for you to find the disk block of that file, okay, depending on whether you have 1 level indirection, 2 or 3. Is that clear? Any questions on this? Okay, so that's your inode structure, and each inode has a number, and that's actually the numeric ID for the file inside the OS. Okay, that's a quick recap of Unix file systems. With that background, or very little of that background, let's talk now about distributed file system. Okay, so what is a distributed file system? So in a DFS, what we assume is that the data of that file system is now stored on multiple disks on multiple machines. Okay, the standard file system, like what you have on your laptop or your phone, the disk is attached to your machine. All the files are local. Right? So whatever you create is local to your machine. In a distributed file system, that does not have to be the case. Your files may actually be stored on another machine. Okay, and you can access them on your machine as if they were local to you, but the files are in fact remote. They could be on one or more other servers. You just access them, and your OS takes care of getting the file for you, so that you don't have to worry about logging into that other machine to access your files. You just access files as if they were local. The distributed file system provides a unified view of all the files across all the machines, making it look like they were local files. But it takes care of figuring out which machine the file is stored on, what disk on that machine, and then what disk blocks of that machine, and so on. Okay, that's the general idea of a distributed file system. And typically, like in any other distributed application we have seen, okay, even in a distributed file system, you will have clients and servers. Okay, servers are machines that have disk space that are going to store your remote files, and clients are machines that are going to access those files, like any client server application. Even our file system is now built as a client server application. Some machines are clients, others are servers. Of course, a machine can be both a client and a server if it allows others to access its disk and it accesses other machines' disk. Okay, but you still have this client server architecture. Okay? So our file server is essentially any machine, one or more, in a distributed file system that has disk space that allows other clients to create, modify, delete files on that disk. Okay? And clients are, of course, machines that are going to access it. Right? So we'll now look at what a file service on a server looks like. We'll talk a little bit about directory service, not a whole lot. Okay? So here is an example of how two methods that a client can use to access files on a remote machine. Okay? So one is called the remote access model. The other is called the upload download model. Okay? In both of these cases, you start off by a server machine that has access to a file, and some remote client is accessing that file. Okay? In the first case, whenever that client wants to do any read, write operations on that file, those operations are sent to the server using, let's say, RPC requests. Okay? A file read is going to become a network RPC read. It goes to the server performs that operation, sends back the result. If you're asking to read some bytes of the file, you send that to the server returns the whatever you requested, and your client will just read it as if it came from your local disk. Okay? So all file IO operations at the client are sent off to the server processes them, sends back result. Okay? Simple idea. That's how any server works. You send requests to the server processes. Okay? The upload download model is different from that architecture, whereby when the client first accesses the file, okay, you basically make a copy of the file and bring it to the client. Okay? All subsequent accesses at the client are made on the local copy. Okay? So first time you do a file open, your server will actually send that file over to you at the client. The client will keep a copy. There's still a copy on the server. No, there's a client copy at the client. All further reads and writes are done on the local copy. When you close the file, any modifications are sent back to the server. So you will see here that there's a file. You bring it over to the client. So now it's labeled old file because that's the most recent copy. All accesses are done here. And then when you close it, you send it back. So there's a new version of that file. The old one is deleted. Okay? Upload download model. Here are pros and cons. Okay? In remote access model, the work is done at the server. In the upload download model, beyond fetching the original file to the client, all work is done at the client. So these IO requests are going to be faster because here these are local disk IO. Here this is network IO because all requests are going over the network. Okay? In this case, okay, you might have a stateful server. You need to keep track of who has opened the file and so on. Here you can make it stateless. Beyond knowing who has a copy of your file, there is no actual state information or which files are open and so on. You just need to know some copies of the files are now currently at client. Okay? From a consistency standpoint, the remote access model is easier because multiple clients can open the same file at the same time. And anytime you make a write to the file, another client can see that write, so long as the clients immediately send their IO operations to the server. Okay? In the upload download model, you can easily imagine that the first client gets a copy of the file, starts modifying it. Now the copy on the server is out of date. It's stale at this point. Okay? If another client tries to access the file, it may still get a copy, but the copy that the server sent you is no longer the most up-to-date copy because that's held by the client. Okay? So dealing with consistency in this case is harder. This works well if typically only one client accesses the file at any given time. It works really well because it improves performance for the client. But if there are concurrent file accesses from multiple machines, this is not going to work well from a consistency perspective. Okay? So here server can be a bottleneck because all operations are being done at the server, all request processing is done at the server. It's a little more scalable here because all accesses are IO, all IO accesses are local, and the server is simply sending files and getting files. It's not actually processing all the IO operation. Okay? So this requires more communication overhead than the other approach, okay, which only is going to move files back and forth. Okay? At this point, these are two abstract models. We'll see how these models are incorporated in real file system. Okay? But by and large, every distributed file system is going to use one or the other approach for providing access to remote files. Any questions on this? Okay, so let's talk a little bit about state and what are the pros and cons of making a server stateful or stateless. Okay, the first thing is, what is the state that a file server has to maintain? Okay, this state could be which files are open and opened by which clients on the network. And a local file system is also stateful, by the way. The OS knows which files are opened by which application. Okay, because inside the OS kernel, there's a file access table. Every time a process opens a file, you keep track of these files are open. These are the process IDs that have opened the file. So local file systems have always been stateful. Now we are asking you, our distributed file system, should we keep state or not, and what are the pros and cons? Okay, so if you have a stateful server, it's going to do the same thing that a local file system would. It will keep track of what files are open and by whom. By whom in this case are other clients on the network, not local processes. Okay, that's the big difference. Okay. In contrast, stateless file server does not keep track of which files are open and so on. And we'll see ways to make the server stateless. So you don't keep any state. Okay, so you don't know which clients are accessing information and things like that. Okay. All information is essentially sent to the server for each request, so that request can be processed, and then the OS and the file server forgets about any client specific information. Okay. So stateless server means that every request has to have more information, because you have to make sure that the server has all of the information needed to perform that operation, including whether the client has privileges to access the file and so on. Okay. In a stateful server, you will only do this check at file open time. When you open the file, it'll say, do you have the proper read or write permissions on the file? Yes or no. If so, you get a file handle. From that point on, you use the file handle to access the file, and the OS is not going to keep checking whether you have permission, because already checked it when you open the file. But if you're stateless, every request you have to perform all of these checks. So requests have to have more information. You have to have more processing done at the server before you let that file operation proceed, or deny it if you're not allowed to do this. Okay? So that's a difference between a stateful and stateless server. So your messages are shorter, they're longer, more processing. Stateless servers always more tolerant to crashes. Okay? You don't keep state, there is nothing to lose. Okay? As far as state is concerned, if you crash and restart. But on the other hand, if you had a table in memory that had a list of all clients that were accessing that file, server crashes, comes back up, you lose that information. Okay? Any state in memory is always lost. Okay? And we'll see that in the stateful server, you can actually make it idempotent. Okay? There's some consistency advantages as well, which we will get to. All right. So upload download model versus remote access, stateful versus stateless. We are just talking high level concepts at this point. We haven't gotten to anything specific. Okay. So with that background, let's look at one specific file system that is distributed. It's called NFS, or Network File System. It's widely used as Unix-like environment. Every Linux machine is going to support it. Mac supports it, actually. So does Windows. It's cross-platform. It arose from the Unix world, and then now it is actually supported by all kinds of platform. Okay? Incidentally, NFS was also the first implementation that used RPCs. Okay? The first commercial implementation of RPCs was to implement this as the distributed application. Then they realized that as RPC is a more general concept, so they actually took all the RPC things and made it its own tool, so anyone could write an RPC application. But back in the 80s, NFS was the first real use of RPCs in the commercial world. They were, of course, present in research papers for various things, but this was how it actually arose. Okay, but let me explain what this picture is showing you. So you have a client and a server. NFS is, of course, has an NFS server. There are clients that are accessing data at the server. That's your server. That's a server disk. Okay, clients can now access files stored on this disk. Okay, that's a simple client there. Client has its own disk, and it may have its own local file system that's independent of NFS. Okay, that's just your local file system. But in addition to your local files, you can access files stored on an NFS server, which in this case is this machine. Okay? And you will see that there is RPC stub at both ends. So if the client is accessing a file stored on the server, it is just going to open the file and try to read or write to that file. Okay, those requests are going to come into the file system layer, and you will have an NFS client inside the OS that is then going to make RPC calls to the server. So if you do a read of a file, the NFS client is going to make a read RPC call to the server. It's going to go over the stub. The NFS server is going to then process it, actually read the contents of the file as requested, send back a response. Okay, so file operations become RPC operation. Okay, now as far as the client is concerned, you will see that it is at least supporting two file systems. It's supporting a local file system that accesses files on the local disk, and it is supporting the network file system, or NFS, that's accessing remote files. Okay, so whenever you are making a file operation on that machine, the OS has to decide, is it accessing a local file or a remote file, and then pass that operation to either the local file system code inside the OS or the NFS client code inside the OS. Okay, because there are two file system implementation in this picture. There's a local file system implementation and there's an NFS client implementation. Okay, both are inside the OS. So each operation has to be then forwarded to one of these two pieces of code, and this is done through a more general mechanism called the virtual file system layer, or VFS. Okay, that's a general layer that all Unix operating systems support, where requests come in, and that virtual file system is going to redirect that request to the right kernel module that implements that file system. Okay, in typical Unix kernels, you don't have two, but you might have many different file system modules loaded. Okay, you might have, let's say, the FAT file system. That's what you have on your USB drives. Okay, that's a completely different file system. There's a piece of code inside the OS that is designed to access files on those types of devices. Okay, you might have a module that is designed to read, let's say, DVDs and CDs. That's a different file system. That's an ISO file system. Okay, that's its own component. Okay, then you have a local file system, which could be ext3, ext4, some Linux file system. You have NFS. So in a typical OS, you have multiple file system implementations inside the kernel. Okay, the virtual file system is an abstraction that sits on top of them and provides a unified abstraction to all the clients. Okay, so the client or your program doesn't need to know what type of device or what type of file system you are using when you try to access a file. You don't do a NFS file open or a ext file open. You just do a file open. The OS is going to take care of figuring out what type of file system this file is stored on, what device is stored on which piece of code inside the kernel to send it on. And that's done by this VFS layer. Think of it as a forwarding layer. Okay? All file operations will come to the virtual file system layer, and it will forward that to the right component. Okay? And furthermore, it will call the right method inside that component. So a file read could be an NFS read here. A file read there could be a ext read here. Or a file read there could be a FAT read to a FAT file system, and so on and so forth. And all of that is done by this level of abstraction that allows you as a user or developer of code to not worry about all this. You just call file open without knowing any of these details. All of that is hard work is done there. Okay? You will see that there's another one here, okay? Because this is also a machine. But in particular, this is useful for the NFS code, because the NFS server is going to receive RPC requests. Okay? These RPC requests are actually file operations on a local file system here. Right? So let's say you get an NFS read from the client, it comes to the server. Okay? The server has to then send it up to the virtual file system layer, which will then become a local read and come back down to the local file system and access the file on that machine. Okay? So even the NFS server in this case is going to use that file system layer to forward that request that came as an RPC as a local file operation to some file system on that machine, and the responses are going to go back. Okay? So that's how you have the ability to support multiple file systems inside the OS kernel, okay? In addition to the two that are shown here. Any questions on this? Okay, so that's our NFS architecture. This is a long table that shows you all kinds of operations that NFS are going to support. Each of them is implemented as an RPC call. We are not going to go into all of these calls, but I just want to provide maybe some insight into one or two of these calls. Okay, you will see the standard one. There's something to create a file, there's open, there's a read and a write. Okay, but there are lots of other ones because you have to do directory operations and all kinds of other things. Okay, but I'll just point to two things in this slide. First is there are two columns here. One is called version 3, another column is called version 4. Okay, what this is referring to is NFS version 3 and NFS version 4. Okay, version 3 has been around for a very long time. It is kind of the default that was used in NFS for a very long time. And then NFS version 4 was the evolution of NFS into a new sort of architecture, and we'll see what the differences are. Okay, until NFS started off as a stateless file system. Okay, the file server was completely stateless. Okay, in the previous slide, then each operation you make just goes as an RPC call. The file system, the server here has no knowledge of what has happened in the past, what clients are accessing what file. None of that is stored at the server. Every RPC request has to have full information about who the client is, what operations they're performing, and then you have to make the checks every time. So there's no state kept at all. Okay, designed to be a stateless protocol. Okay, that's how it was designed for 20-30 years. Okay, then NFS version 4 came along and they said that there are some limitations to the stateless model. There are many advantages, but there are some limitations. So they made the server stateful for the first time in a very since it was designed. Okay, NFS went from being a stateless file server to a stateful file server. Okay, this meant that there are certain things that will change in how you support file operations, but we'll see that there are some advantages of this change in the subsequent. Okay, in particular, you will see if I just point to one row here, that's the open. Okay, that's what you call when you open a file. Okay, you will see that version 3 does not support open, but version 4 does support. Okay, you might say, why is that? Okay, typically on a local file system, you have to first open a file, then only then can you access it. Right? When you open the file, the OS is going to perform some checks, is going to create an entry for you in the file table, which is the state of that file, and return a file handle. Okay, that's what an open call does when you open a file. I assume that you know some of that. Okay, now since NFS is a stateless server as of version 3, okay, there was no concept of doing an open. Instead, there was another call called lookup, which was essentially going to just say, can this client access this file or not? Okay, you just check and you return, but no state is kept on the server saying I ever performed this check. Okay, so it was done by the client. So you just did a lookup call, and never an open call. But as of version 4, because it became stateful, they actually introduced a specific RPC for that call where you could open and get a file handle, and the state would be kept at the server saying this file is opened by this machine on the network and so on. Okay, that's just one very simple example of what happens when you go from a stateless to a stateful server. Okay, essentially, open is where you keep maintaining state in your file system. It was not supported in version 3, but now it is supported. Okay, and then there are all these other calls which I will not go into. You don't need to worry about them. But I'll talk a little bit about this open and whatnot in the next few slides. Okay, are there any questions on what I just said? Yes. Okay, question is the NFS client and server implemented as a user space process, or is it implemented inside the kernel? The answer is that it is an in-kernel implementation. It's not a user process. Okay, in most operating system, the NFS code is going to reside inside the kernel, like any other file system code. Okay, if you are talking about user space file systems, which are designed more as a research thing, that's not what this does. This is a standard file system that's implemented inside the kernel. Just happens to be a distributed file system. That's all. It's still in an OS thing. Okay. All right. So now let's start looking at how some of this is going to be used in NFS. So here is what you are going to see between the client and the server. the client opens a file and then does a read. So you do a file open, then you try to read some data from the file. Okay? When you open the file, because NFS version 3 does not have the concept of an actual open, you still need to check whether the client is allowed to open the file, whether you have the right permissions. Right? The way you are going to do this is through a lookup call. The lookup is going to provide information. Here's a client. This is the user ID. Can this client open and access the file? Does the file even exist? Okay, so because if you give an incorrect name, you're going to get an error. So the lookup is going to look up the name, look up permission, and send back a reply. Okay? And if the lookup succeeds, then we just tell the client that the open has succeeded. Okay? Client is still going to do an open. Client as your program is still going to do a file open, but internally, what the NFS client is going to do is do a lookup on behalf of that open, because we don't actually support open. Okay? And then you send a read. That's going to become a read RPC. It goes to the server, sends back a result. That's version 3. Okay. Now in version 4, you have the open call. So you will see that some different things are going to happen. So you open the file and you try to read it. What the client is going to do is first is going to send a lookup request saying, can this client even access the file? Okay. And then it's actually going to open the file, okay, which will allow you to keep state at the server, and then you will do a read. Okay. So you have now an open, explicit open in addition to the lookup that you're going to perform. That's number 1. Okay. Now, but if you look at this figure, you will see that there's only one RPC going and another one coming back. And the reason this is the case is NFS version 4 supports what's called a batched RPC. Okay. The first time we have seen a batched RPC, also called a compound RPC. Okay. So essentially, a batched RPC is multiple RPC requests sent as one request. Okay. So in that batched RPC, you have made a lookup request, an open request, and a read, all as a single RPC. Okay. When the RPC call goes, the server is still going to perform all of that, but you're not sending a separate request for each RPC. You are batching them and sending them as a group. Okay. And then having the server perform all of those operations, which is why you see that there's only one of these arrows going from the client to the server and a response coming back. And you'll see that you do a lookup, you open the file, you read the data, and send it back. Okay? So batching is supported as a performance optimization. It's not a requirement. Okay? The NFS client in this case could have made 3 separate calls, would have worked perfectly fine. Okay? Just to reduce the network overhead and improve performance, you can batch. That's an optimization that they put in NFS version 4. So 1 RPC per operation in normal NFS version 3, multiple operations per or multiple RPCs in operations per RPC in version 4. That's batching. Okay. Question, yes. Okay, question is, why is the lookup triggered? Is that your question? Okay. So how do you access a file in any program, Python or whatever, Java? You open the file, then you do a read on the file, right? So when you open the file, okay, that's essentially going to eventually go to the OS as a system call. That's going to be an open system call. Your application level open in your Python or Java code becomes an open system call at the OS level. That's going to go to a virtual file system layer. It's going to come to an NFS client, and the client has to service the open. But version 3 does not have a concept of an open. So instead, it's going to send a lookup operation to the server saying the client wants to access this file. Is the file name valid? Is the client allowed to do it? That's all you're going to ask. So that's your lookup. Okay? And then you get back a response, yes or no. If it's a yes, your open call will succeed. Okay? And then when you try to read the file, okay, that's just another thing in your program, then you'll get another read system call that's going to trigger another RPC. So these 2 operations are actually a result of 2 specific operations by the program, first to open the file and then to read some data from the file. Okay? We are only showing what's happening inside the kernel, but there are operations that the user or their program is doing that triggers all of this. Okay? Any other questions here? All right. So that is NFS version 4. Let's now talk a little bit about how the client is actually accessing data stored on other machines. Okay. So here we have 2 clients, client A, client B. Those are local machines. What's in the middle is the server. Okay. Now, what this tree-like structure that we see are essentially directories and files. Okay. Square means a directory, circle means a file, okay, in that directory. Okay. Now, the assumption is this server machine is going to take some of its file and make them available to other machines. Okay. Server can select which of its files it is exposing to other machines. There's no requirement that every file on the server be made accessible to other machines. So you decide as a system administrator or a user saying, I want to essentially share this directory or this part of my subtree with other clients. Okay. So in this case, you will see that there are this is a mail server presumably, and there are a set of mailboxes. Okay. And there's one mailbox per user. Okay. So that's how your mail server would work. There will be a directory where your mail is stored. There's a file which is your inbox. Right? Your inbox could be represented as a single file per user. Okay. So now you've taken this subtree, okay, and you made that available. And everything outside is not made available. Okay. Or you could have a set of user directories, okay, which you can also export. So if you go to the Ed Lab, okay, when you log into a machine, you can see your home directory. Okay. If you log into another machine, you can still see the same files. The reason is that there's a file server, and it is an NFS server where all your files are stored, okay, and your home directory is now actually made accessible by that server to all the Ed Lab machines. So when you log into the machine, okay, you actually see your files, but the files are stored somewhere. And since the same set of files are shared with across machines, you can see those files on any machine. Okay. Same is true here. Okay. So if you actually go and export something like /users, those are user home directories. If you want to then expose mailboxes, then you have to expose the mailbox directory. Whatever you want to expose from the server, you can do that. And then the rest of those files are not accessible. Okay. Now, the way this is done is to something called a mount protocol. Okay. A mount protocol is used by NFS. For the server uses it to say, these are the subdirectories on my disk that are accessible to others. And it's used by the client to actually access one of those volumes. Okay. The server exports one or more volume. A volume is essentially some subtree rooted at some directory, and everything in that subtree is accessible if you export that. Okay. And then the client is going to actually run mount, say, I want to mount this users. You will see that you have mounted this users, either home directory or mailbox is here. Okay. So this triangle, whatever is in here are not real files. Those are files visible on client A, but those are remote files that are actually stored on the server. Okay. So when the client tries to access any of these files, the NFS client code will send RPC request to access the file from the server. Okay. Whatever you see in the dotted area on client A and B are essentially files or directories that are mounted from the server using the mount protocol. Mount protocol is just a way to access a directory and its subdirectories on the server. Okay. And you have this mapping that you say all the files here are mounted on /remote/vu/mailbox. Okay. So you can now get all of those files accessed on these machines. Okay. Is that clear? Yes. Go ahead.
Are they all going to be able to access?
Okay. Question is, client A can access some files in that mounted directory. Client B can also access files in that mounted directory. Can you see all of those files? That's your question, right? What you can see and what you cannot see is going to be controlled by file permissions, right? Typically, you don't want to see some other user's mail. That is a privacy problem, right? Because you don't want to expose data that's personal. So just as you would do this on your machine, on Unix machines also, you set the right permissions. If you say these files are accessible to other users, you can make them readable or writable, in which case other users can see them. If you remove those permissions, only you can access them, others cannot. The same is true in NFS. There's nothing has changed. You could have asked the same question even if this was not NFS. You can say two users log into client A, can they see each other's file? The answer is depends on whether they have set the right permissions which allow them or prevent them from seeing it. Same is true of mounted files. Okay, you can of course make files visible to other users across machines, or you can say no, right? And then the OS will essentially prevent those users. Right? So file sharing can be done in distributed file systems in the same way. Yes, question. Okay, question is, does mounting create a list of files stored on the server, or are you always going to look up files on the server? The mounting is simply a mapping. Okay, it's not going to create any list. Mounting is simply a mapping saying when the user looks at this directory, okay, that directory is actually a mapping to this directory on the server. You just have that mapping inside. The client OS is not going to know what is stored in that directory. So when the user tries to access anything inside the directory, all the operations are sent to the server, and whatever response comes back, you can see those responses. Okay? So it's not a list, it's simply a mapping that tells the OS that when the user program tries to enter this directory, forward those requests to the server. That's all it is. Okay? And that's what the client will do. It'll forward it through lookups and whatnot. Yes. Okay, question is concurrent access possible in this model? So there are two types of concurrent accesses that I'll talk about. Concurrent access. So first of all, concurrent access is of course possible. You can have this client and that client access files in that directory. I mean, that's what happens in your ed lab. There are all kinds of user directories, multiple users are logged in, they're all working on labs and so on. So that is concurrent access to files that are stored on your file server. Okay, that's one. The second way to interpret your question is, can you actually concurrently access the same file, not the same volume, but different files of the volume? Even that is of course possible, but if you do that, then you need additional mechanisms like locking to allow that to be done in a reasonable way. Otherwise, you're simply going to overwrite each other's data. We're going to talk about file locking in just a moment. Okay? That is true even for local files. You can have two programs open. You can even try this. Okay? Create a file, write two Python programs, open the same file and try to read or write. You will overwrite each other, right? If you're not careful. So even in local file systems, if two applications open the same file, you have to implement locking. Okay? Otherwise, you'll get incorrect result. Okay, that is especially true for this example because you're talking about mailboxes, right? So mailboxes actually have to support concurrent access properly, and the reason is you will have at least a mail client that's trying to read from your mail, or you might be deleting mail, so you're reading or writing to a mailbox. But there is also the mail daemon that is delivering new mail. Right? So a mailbox is a buffer where your IMAP client or your machine is simply trying to read data, which is mail, and there is a mail server that is actually delivering new files. So you can actually get concurrent accesses from that perspective. Okay, it's a hard problem. If you don't do it well, you will get corruption. Right? So that's something you have to keep in mind. Okay, that's mount protocol. Here is essentially a problem that arises if you do mounting. And here's a recursive mount. Okay, so what you have here are two servers. In the previous case, there are two clients, one server. Here you have one client, two servers. Okay, server A, server B. Okay, so what has happened is server B has taken this part of its subtree, what you have shown here, okay, and it has made it accessible to server A. Okay, so on server A, you have these local files, but then server A can also access server B's files, which is essentially the install directory. Okay, so that's accessible on server A. But then we assume that server A has essentially taken what's in the outer triangle and made it accessible to the client. Okay, that's your packages directory. Okay, so we made that accessible to the client. Okay, now the question is, when should the client now get access to B's files or not? Because B's files are now resident as a subdirectory in the packages volume that you exported to the client. Okay, so should you allow transitive access where server B makes some files access to A, okay, server A makes some files accesses to a client, but the files are made accessible include other files from another server, and should you allow that or not? Okay? So there are two answers to this question. The first is, until NFS version 3, there was no notion of transitive access because the trust model was between a pair of machines. Okay? If server B trusts A and say, you can access my files, server A shouldn't be able to re-export those files and make them accessible to someone else. Then you lost control of your files. You made it available to someone, they went and made it available to someone else, and you don't have any control over it. So until version 3, you said trust model can't be broken. That's a security problem. So even if this client tries to peek inside these files by sending an RPC request to A will deny it, saying those are some other machine's files, so you can't look inside. All I did was I made my files available to you. I'm not going to let you access someone else's file that are accessible to you. Okay? That is essentially version 3. Now version 4 has actually relaxed that, and it has allowed recursive lookups, but you need to explicitly allow this. You cannot just allow simple mounts and then allow re-exports. Only if you say this can be re-exported, you will allow this recursive mount. Okay? But so version 3 had a very clean trust model. Is pairwise. I trust you, you can access my file. You don't make my files accessible to third person. That's not allowed. Okay? You can make your files available to someone else, but that's not my problem because there's trust between you and a third party. Okay? But V4 has allowed some notion of recursive mounting for various reasons. Okay? So they allowed a more relaxed trust model in this regard. Is that clear? What the issue is and what kinds of things are allowed and disallowed? Okay. The last thing I'm going to say about mounting is what is called auto mounting. Okay, auto mounting basically means create mappings on demand. Okay, because let's say you have a server. In this case, this is the machine, that's the client machine. Let's say this server has account for 1,000 users. Okay, each of them has a home directory with files on that server. Okay, now you could, on this client machine, create all of those mappings ahead of time, saying when Alice logs in, her home directory should be mounted at this location. When Bob logs in, their home directory should be mounted on this other location, /home/Alice, /home/Bob, and so on and so on. So you could create all kinds of mappings a priori, so that whenever any of those 1,000 users logs in, the mapping has already been created. Okay? But what auto mounting says is that is wasteful. Those users may never log in. Why should I create the mapping beforehand? Okay? I'll just keep that mapping in a file, and whenever the user logs in, I'll read that file and create the mapping on demand and mount on those volumes on demand until the user has logged in. After they log out, I'll remove the mapping and the files become inaccessible. Okay? This is called mount on demand or auto mounting. It's a mechanism that's an optimization that saves you from creating large number of mappings on clients, and maybe those users never access those machines. Only when you log in will you create that mapping. Okay? So you don't even have to actually say only when you log in. Even if you actually try to access a directory, okay, that's an NFS mount, you will do auto. If you have an auto mount setup, it will mount on demand. Okay? So not just for login directories, but any volume. Whenever you access it, you will get mounted. When after you stop accessing it after a while, it gets unmounted. Okay, that's an auto mount feature. I think the EdLab does use it because you can actually see your lab mate. You log in and you actually look at what files are mounted. Okay, you will see that there are some that are mounted, and you have your lab mate login. You will see that their directory gets mounted on the fly. Okay, that's an example of auto mounting. Okay, so having said that, now let's look at what the NFS interface is for it to support all kinds of other file systems. So one thing to remember is NFS is not a typical file system in itself. It's a layer that sits on top of an existing file system. Okay, if you go back to maybe several slides ago when I started with NFS, you will see that there's an NFS client and an NFS server, but that is layered on top of a local file system. Okay? So what NFS simply does is it takes a local file system and files on that file system and makes it available to anyone you want to share it with over a network. Okay? It's not a full-fledged file system in that it does not directly manage anything on disk. It is just sitting on top of another file system. So in some sense, you can take any file system of your choice, put an NFS layer on top, and suddenly that file system has become a distributed file system. So now I can share the files from that machine onto other machines. Okay, so that's something you want to keep in mind. So NFS is essentially a layer that sits on top of other file systems. Okay, in Unix it will sit on top of ext3 or ext4. On Mac it will essentially sit on top of HFS. It also runs on Windows, so you can run NFS on top of NTFS, and then you can essentially share NTFS files with other machines and so on. Okay? So then the question is, what is it that NFS requires the underlying file system to support for it to allow it to be exported? Okay? Because you want NFS, as I said, is a layer that sits on top of other file system. So you want to say it will only work with file systems so long as they have this functionality, right? So that it is NFS compatible in some sense. Okay? So these are operations that NFS requires the underlying file system to support. Everything else is an optional operation. Right? So how the way NFS was designed was, it said it had very bare bone requirements on what it expected from the underlying file system. So long as the underlying file system did some very basic things, you could take it and you could re-export it. Okay? Or not re-export it, you could export those files to another machine. So you'll see that so long as the file system has a type attribute which says, is this a file or a directory, it keeps track of the size of each file, it keeps track of the time of the file when the file was changed, and it essentially has an ID, which is like an inode number for a file. That's all it requires the file system to support. Okay? So you will see that that's a very basic set of requirements. A lot of what you actually see in a file system is not even required by NFS. Okay? So for example, you don't need the file system to have an owner for NFS to be compatible with it. Right? Typically, a file has an owner associated with it. Okay? Even if the file system doesn't support it, NFS will be compatible with it. Okay, so what that means is, if you have a USB drive, which is the FAT file system, FAT doesn't have a concept of an owner, which is why you can put a USB drive on your machine, copy some files, give it to someone else, and they can access everything on a USB disk. The reason is that there is no owner, there are no permissions, you can freely share files. Even those file systems can be shared on NFS. Okay? So you will see now that here are additional attributes which makes NFS perform better. Okay? What I showed you on the previous slide are mandatory attributes. The file system must support these functionality for it to work with NFS. These are additional functionality that would be nice to have. Many modern file systems will support this and many other things, but it's not required for that file system to work with NFS. So here you will see other things like, okay, if the file system supports owner of a file, that would be nice. There's an access control list, which means I can now read, write, execute permission. That's good. So NFS can control what others can access and so on. And then you can have file handle, file ID, creation times, and other things. Okay, so you expect that most file systems will have this, but NFS doesn't even require it for it to be compatible with the files. This was done to maximize compatibility with all kinds of file systems that were out there. Okay? And NFS was designed in the 80s. So those days you had all kinds of bare bones file systems which didn't have what modern file systems. Is that clear? Okay. All right. So now let's talk a little bit about semantics of file sharing, how NFS deals with consistency and things of that. Okay? So here, this slide is supposed to illustrate how local file systems differ from something like a distributed file system, because you have now multiple clients accessing files and so on. Okay? So on a local machine, when you read a file and then you write to the file, whatever you're written to the file becomes immediately visible to other clients. Okay? This is called Unix semantics. Okay? So you open a file, maybe you write something to a file. Okay? Another process opens a file immediately after that. Whatever you've written is visible to that other process. Okay? Immediately. Okay? That's what will happen on a local machine. That is not the case on a NFS. And here is an example of why that is the case. Okay? What you have here is a file server in the middle, the client 1 and client 2. Okay? Initially, the file has, okay, let me actually do this example first, then we'll do the other example. So a single machine, okay, you have an original file that has 2 characters, A and a B. You just wrote 2 bytes to the file, A, B. Process A is going to open that file and write C, append C to the file, So the file contents becomes ABC. Okay. Then process B is going to open the file, and what it will see in the file is ABC, because that's what has just been written. Okay. That is what we call mean by Unix semantics. So any writes are immediately visible to other client. Okay. Here is what will happen in the NFS case. Your original file AB is stored on the server. Okay. Because now your process A is now running on a different machine. Here both processes are running on the same machine. Your process A runs on machine A. It opens the file. It sees AB. Okay. Then it's going to write C to the file. So the file becomes ABC. But in NFS, you have caching as a performance optimization. So the file is the value that you wrote C is actually cached on the client. It is not immediately sent to the server. This is done as a performance optimization. Okay. So for this period of time, the file has actually changed. It's ABC. The server does not know about it because the client has yet to send its RPC request of the write. It has just hit the cache. It's not been flushed to the server. Okay. So now if client machine 2 goes and opens the file after that C was written, it is going to see the old version of the file. So you see AB. Okay. Then from an NFS perspective, that is okay, because that's what NFS says are its consistency semantics. What NFS implementations do is they say it can take up to 30 seconds for any writes at a client to be flushed to the server. Okay. That's not a requirement, but that's how many implementations work. They keep a big cache. All the NFS writes are actually going into the cache. Every 30 seconds to flush them to the server. So there may be a period of time until when what is stored on the server is out of date. If some other client, and there was that question whether this concurrent access, some other client concurrently opens the file, you'll get stale data. This will never happen in a local file system, because in the local file system is only one copy. It's inside the OS, okay, and you will always see the writes because that's already hit the OS. That's why another process actually opens the file, the OS already has all of the changes in the file. Okay. So this is a problem, but that is the cache consistency. So it's a loose semantics, not strict consistency. Okay. If you had strict consistency, as soon as you had written it, you should have sent it off to the server. That is not what NFS does. It's much weaker. In fact, it is called NFS semantics, where you will have an arbitrary delay that's implementation specific, actually. That may take some time for you to flush these results. Okay. Is this clear? Okay. So if you are doing something on an NFS server, you should know if you have two clients trying to access it. Maybe you open the file on a desktop and try to open the file on another laptop. You try to make a change. Your other machine is not going to see it immediately. It will take some time. Okay. So which you will not have if you have two windows open on the same machine and you're trying to access the file. That's not what you expect. Okay. This is what will happen here. Okay. So that brings us to all kinds of semantics that file systems support for what happens when a write is made to a file and so on. So Unix semantics says every operation to the file is immediately visible to all processes. Okay. That's almost like strict consistency, but it only works on local machines. Unix semantics is hard to implement on other multiple machines. So what NFS supports are what are called session semantics. Okay. So it actually does better than session semantics, but at least does that, which is no changes are visible to other processes until the file is closed. Okay, so you can start open the file, make changes. They're all cached locally. When it is closed, NFS guarantees that the file will be flushed. But until it is closed, it's implementation specific. It puts a 30-second delay, but not required. Okay, you could have just not flushed anything, waited until the close, then sent it. But what it actually requires is session semantics. It does a little better than that by sending the changes every 30 seconds, not waiting for the close. But if it waited for the closed, that is essentially a pure session semantic. Okay. Now you might remember when we were doing transactions, I explained the workspace model, which was like this. You made a copy, you made changes. If you have to commit, only then you send the changes. Okay. Session semantics tries to approximate something like that. Of course, these are files, not transactions, but that's what is happening here. Okay. Then the third one is called immutable files. Immutable file says that once you open a file and write something to it, and after that you can't modify the file. If you want to modify the file, you have to create a new version and write the changes to that new version. So this is good for versioning, where each change creates a new version and previous versions cannot be changed once they're created. These are called immutable files. Okay? They are used in many good contexts where you can keep every version of the file, so you can use them in versioning file systems and so on. So no updates are possible once you create. The file is immutable. But of course, you can write to it. The way you do it is you create another copy, which is the next newer version, and write to that version. Okay, so that's immutable file. And then there are certain file systems, not all, but some, that are going to provide you transactional semantics. Okay, you open a file, you make some changes. Okay, if you want to commit or close the file, then the changes become visible, or you can throw out all the changes, undo like it was a transaction. Everything you did is gone. It looks like you never made those changes. So you have the ability to undo until you commit. So that if you have that, you have transactional semantics. Those are typically supported in databases, but there are some file systems that have started supporting transactional semantics as well. Okay? The most common one for local file systems, Unix semantics. For distributed file system, at least session semantics, and some file systems do immutable files, transactions, and things of that sort. Is that clear? Okay. All right. So a few more things here. We'll talk now about file locking, because that was a question that was asked. What happens if you try to open two processes, open the file? Yes, no question. Okay, question is in session semantics, how do you prevent overwriting or consistency? Now, the file system is going to say this is what it supports. If you want to have concurrent access and so on, you have to build it at the application level. Okay? The OS is not going to help you in this case. If you want to make changes visible, you might have to explicitly flush after every change. There are system calls that force you to send data. Okay? You'll have to put that in your code so that you make a write. You want some other machine to see it, you have to explicitly flush so that you go and send it off to the server and so. So it certainly complicates matters, because this is a very loose consistency semantic. If you want concurrent access, want to see every changes, it's not going to give you that. Okay, that's going to be a problem. Okay, yes, question. Okay, that's a good question. The question is, after the server sees changes, since the file may be cached at other locations, is the server going to inform other clients? Right? Good question. You should expect that the server should do that, but NFS doesn't. Okay? NFS gives you very weak semantics. It says flush changes whenever you want. Even if other clients are accessing it, they are not going to do it. At least version 3. Version 4 has some benefits over there. Okay? The reason you cannot do that, okay, even if you wanted to, is because remember I said it was stateless. Okay? Stateless means I don't even know who has the file open, what they have cached. Even if you sent me some changes, I wouldn't know which other client to inform, because I don't have any state. Okay? When you make a thing stateful, then you could even ask that question, should I inform someone? Because then I know who has opened the file, which machines have the file open. But version 3.2.1 never kept this information. So you couldn't do it. Fundamentally, it was not possible. Okay? Other questions? All right. File locking. Okay, what does file locking mean? File locking is not an NFS specific thing. It's just a file system operation where you can actually take a lock on the file, okay, and then prevent other processes from not accessing the file. Very similar to locking in threads. You can actually lock a file. Okay? You have read-write locks. So if you take a read lock, no one else can take a write lock, but others can read. If you take a write lock, no one else can read or write. Okay? File systems support locking operation. Okay? Now, since NFS until version 3 was stateless, okay, you could not also support locking, because you can't keep track of who actually has the lock. Okay? Lock actually is a stateful thing, because at least you need to know, is the lock available or free. Okay? If you can't keep state, then you can't even implement locking. Okay? After version 4 came along, NFS added locking as a feature. So long as the underlying file system supports locking, version 4 will also support lock. Okay? And the locks are actually more fine-grained. Okay? You don't have to lock the entire file. You can lock a range in a file. You can say lock bytes 10 to 20. Okay? So only those bytes of the file are locked. other bytes can be accessed. So you can decide which part of the file you want to lock. So if you think about your lab 3, okay, if you are actually updating some entry in a catalog, and while you're updating it, you don't want some other threads to read it, you can only lock that entry, not the other entries. Other entries can be read and so on, right? So that's useful so that you don't have to do coarse grain locking of an entire file and things of that sort, right? So you can create a lock for a range of the file. You can remove a lock. You can renew a lease, okay? Because remember, if you have distributed file systems, a client takes a lock, client crashes. Now what? Right? So the lock is going to be held forever, and then that part of the file will never be accessible to anyone. So you don't want all of that. So you essentially give a lock for a certain amount of time. Okay? The client crashes, eventually the lease on that lock will expire. Lease says that you are locked for a certain amount of time, not forever. Okay? If you want to keep the lock beyond that, you have to renew the lease until you are willing to release the lock. So this allows you to do better crash of recovery, where if some client disappears or crashes without releasing the lock, after a while the lock will automatically get released because the lease has expired. Okay? So there's a renew operation for locking, which is important here. Otherwise, you would have deadlocks or other problems. Okay? You create a lock on a range of the file. You can also test the lock before taking it, so you don't have to block. Okay? It's like a poll saying, is this lock available or not? Okay? So that's your lock T operation, lock use, unlock. Okay? So various kinds of locking functionality that is supported in NFS. Okay, the question, yes. Okay, question is it non-blocking because you only block certain parts of the file? Is that your question? Yeah, so the way you want to think is a file is a collection of resources. You can take a lock on only subset of the file. Okay? If you're locked certain subset of the file, you can freely access other parts that are not locked. Of course, if those other parts have concurrent access, you should take a lock. But maybe only the first 100 bytes are accessed by multiple processes. So you only put a lock on those bytes, and others maybe access the only one process. No need to lock, right? So you can decide how to use locking. Okay? Now, if you take a lock, of course, it's blocking if someone else comes and tries to grab a lock on it, because it's like any other lock. Okay? Yeah, so question is, does NFS keep track of all of the lock? Because it is now stateful, it can keep track of it, right? Version 3 didn't support it, but now you made it stateful. So now I can keep the lock state saying which parts of the file are locked, who has locked it, how long is the lease given for that lock. Once the lease expires, lock is automatically released. All of that can be done. Okay. Any other questions? All right. So there are other concepts in version 4 which are built on top of locking, which say if you have certain types of locks on a file, if some other process comes and tries to access that file without taking a lock, what should be allowed and what should not be allowed. Okay, so what is shown here on the top, or each of the columns, are what is called the denial state. Denial state means deny that operation. And then what is shown in the rows is what operation is a client going to perform. Okay? So if you see read here, that means some client is trying to read, and the column says has some other process taken a lock that denies that operation. So if there are no locks at all, which means there's no denial, then all operations will succeed, read will succeed. If there's a read denial, which means you're taken a lock which prevents that read operation, then the read will fail. Okay? But writes, if you have only write denial but no read denial, then the read will actually succeed. If you have this essentially taken a global lock, you're denying all operations, then the read will fail. That's how you want to read this table. So in the columns are what the lock that has been taken is called also reservations. So what type of reservations you have on that file that you deny other operations from succeeding. And then if you're a certain type of denial, those operations will actually fail. Okay? That is essentially what this says. And this is doing the opposite. If there is certain operations being performed, If you try to take a reservation, then what will happen, right? So you're already reading the file, some process, and some other process goes and says, I want to deny read access. You say, no, right now there is already a read operation. I can't deny it. Only if no one else was reading the file, can you say, I want to start denying reads on that file, or I want to deny writes on that file. Okay? So this is a complementary concept to locking, where you take what is called a reservation rather than a lock. A reservation says, I reserve this operation for me, and you deny that operation for someone else. Okay? So I reserve this file for reading, so no one else can read. I have reserved this file for writing, so others cannot write. Or I reserve this file for both reading and writing, so others cannot read or write. Okay? So this allows you to also perform concurrent accesses using this notion of reservation rather than doing explicit locking. These are two complementary features in NFS. Locking is one way to do it. That's more traditional. Reservation is another way to do it. Both give you the same concept where you can control when two processes or more than two try to access file, who gets to do what. The one that holds the reservation gets to perform the operation, and then it can deny that operation to other processes. Okay? That's the basic idea of reservation. Okay? Again, it's also supported in version 4 because reservations are stateful. You need to keep track of who has reserved the file for what type of operation. Okay? And that is essentially what is done here. Okay, so I'm going to talk about caching very quickly, and we run out of time. We'll continue next time. I already showed some of this earlier, or talked about it at least. So what you have in NFS is a server and a client, but the client is going to, because you are essentially sending all operations to the server, okay, it is going to keep a cache of the recent operation so that any subsequent operation on the same part of the file can hit the cache instead of going back to the server. So it's a performance optimization. Recently accessed part of the file are cached locally. Okay? Now, because of this, your cache consistency has a problem because you added a cache, so you have to keep it consistent. And as I said, in NFS, the consistency semantics are very weak. The NFS specification never said anything about caching, so it never added any requirement for cache consistency. So this is now an implementation detail where the developer decides what cache consistency to pick, and almost everyone decided to go for weak cache consistency, which means that when the client writes to the file, it will write, and it's an NFS file, it will write to the memory cache, and the NFS client at some later point will take data from the cache and flush it to the server. Okay? That means that there is going to be stale data at the server for some period of time. Typical implementation have a 30-second delay before they start flushing data. Okay, so you are going to have an odd consistency semantics where files can be stale for up to 30 seconds at the server. The client is fine. Okay, it already has the recent data, but the server is not. If somebody else accesses the file, then you will not have that. Okay, the most recent one. Okay. All right, so we ran out of time, so I'm going to stop here. We'll continue the remaining slides of NFS and